Yes, thank you for the introduction. Good evening, everyone. I'm sorry, I'm the last burden between freedom and attending this talk, but I try to keep it short. So, yes, my name is Sanjay, and I work as a researcher at VITO within the Energy Systems and Component Optimization Group. And today I'll be talking about enabling topology optimization for incompressible fluid flow problems, including heat transfer within SU2. To start with, I would like to answer the question, which I think is oftentimes most important, is why? Why do we even want to do this? To draw this attention, I would like to focus on three main aspects. I think first one, everybody in this room is well aware that if we want to decarbonize our industry, a major player is how do you meet thermal energy demand. That means we need to optimize the thermal energy systems, but also redesign them. That brings me to the second point. That means we need to be able to find solutions that can be quickly tailored to a specific application, and I can adjust the objectives as per my requirement. And finally, we don't want to limit ourselves to the conventional designs. We want to go out swim in the ocean, not in a bowl. So we want to explore the unconventional designs. So one possible way to do this is using topology optimization method. Now, just to make sure we are all on the same page, what is fluid topology optimization? So you can consider this domain where the fluid is coming from the left and is exiting on the right. And we want to design a system, which in this case could be, for example, minimize the pumping power. Now we are all from this shape optimization kind of background. So then you can start playing with these edges, although this will not be a very great starting point, but nevertheless. However, in topology, we do not care about these domains. We consider this entire thing as a base of a puzzle board. And we essentially have two puzzle pieces, solid and a fluid. And topology optimization tells you how can you place these individual puzzles so that it can give you a design that minimizes your objective function. So now coming to our objective of this work. So topology optimization within fluids exists for quite a long time, but we want to enable this methodology within SU2 so that we can design actually engineering systems using this. In order to achieve this big objective, we have made ourselves three development phases. First, only laminar flow, then turbulent flow using ramps, and then finally also including the heat transfer. And for each of these development phases, we have three milestones to achieve, which is code, which equations needs to be modified, verify, and then actually put it in an optimization framework to see if it actually produces a design which is usable. So let's start with the code. So understanding what is the foundation of this method, starting with the phase one. So we can start with what type of topology. So there are many different ways you can deal with this. So here we're dealing with what is called as density-based object optimization. You have a domain where you have a fluid, you have a solid domain, and we have our well-known previous flow equations. What we need to do is we just add an additional source term, which is nothing but as a flow restriction. And wherever we have a solid, we turn the source term off. Wherever the fluid, we don't do anything. In theory, some, but we cannot have a binary switch when we are trying to solve a mesh. So what we do is we introduce a field variable called as porosity. Here it is epsilon. And depending upon what porosity value is there, you introduce this additional source. So this is basically the foundation of this method and is also what is phase one. In phase two, we take a step forward, having the turbulence as well. So in this case, we consider the SSTK omega model. So we have a standard equation. We do a similar type of trick. We add additional source terms to both the energy, the dissipation rate. But however, we do need to take care of the boundary condition here because in the boundary condition, you have the wall distance. And in topology, your walls are never defined exactly and they're constantly changing. An approximation that your wall distance is roughly can be approximated by your mesh size, which is an approximation that works. And here is an example of how does the results look like. First, we focus on the positive parts. So we see that it is actually able to capture where the most uh, turbulent kinetic energy is the highest, so we are able to focus on that spot. But the negative part, we are actually trying to simulate something which doesn't exist in a coordinated case. So it doesn't quite accurately capture everything, but nevertheless, it does give us what we want to achieve. That we do can consider how does the turbulence will affect our design. And with this, we go to our final phase, which is including heat transfer. So we look at the energy equation. So we introduce the modifications where now your thermal conductivity is also a function of your field variable porosity. And what do we do is that depending upon whether you are in the fluid or in the solid, you change your thermal conductivity. And here for the source term, it's a bit of a trick that we're trying to play because in three-dimensional world, you don't need to do anything. But let's say if you want to simulate a heat sink in a two-dimensional plane, you do need to introduce some sort of a heat source. That's why we play this rig in a two-dimensional phase. And in order to test this, we did a simple case where you have the fluid domain and the solid domain, and we solve it with the CHT and with topology, and this is the result. So on the left is the velocity field, so we can see in the solid we are able to make almost zero velocity. But if you look at the temperature field, again looking at the positives first, the slope of these 2 points match. That means we are able to get this thermal conductivity variation, but the temperature in the topology is much lower. That means we are still doing some convective heat transfer in the solid part, which should not be there. Nevertheless, this does give us a promising start in order to design the heat transfer problems using topology. So with this, we can look at what did we actually do in the code. So this is currently available on the feature chorus media top-up. The legacy code was by Thomas. So we extended this to energy equation and also turbulent source terms. And these are, let's say, the three main important classes that we have modified. And just to highlight what actually is happening in this alpha term is that we are controlling this with a tuning parameter called as Q. So this is what user can control from the config file in order to determine how stiffly you want to control or penalize your solid with respect to. So with this, we can move on to actually the verification. So first step is making sure your adjoint sensitivities work. So we consider a simple domain, which is where no problem in, let's say, topology literature, where you have two inlets, two outlets, and you solve it for a turbulent domain. And this is how the adjoint sensitivities look like with respect to the final difference. So we are able to get within 0.1% relative difference, which is good enough for our cases. So that means we are able to get the correct sensitivities. And then we do some couple of very famous cases. First one is the tank pipe. So you have a flow coming in from the left and it exits in the bottom. And the diffuser where you have this entire plane as an inlet and you have a smaller outlet. So in this picture, the light regions is solid and the dark regions will be fluid. And if you see what this topology do, it will give you a design out situation. So amount of energy that the fluid has to spend in order to go from left to right in both ways. And both the designs match quite well with the literature. Moving on, we have this one piece of puzzle landing, which is we actually want to design these systems. We don't want to do only theoretical cases. So here we are showcasing two design cases. First one is a manifold problem. So we have a flow coming in and it gets distributed to multiple pipes, and then it has to be collected and sent back again. And we want to optimize both inlet as well as the outlet manifold simultaneously. And for the second uh, design case, we are considering a heat sink. So you have flow coming in and you have, let's say, power electronics or batteries, and you want to cool the surface down and the fluid exits. In this case, we only consider a 2D. So let's see for the first design case. This is a very cool graphic. I really like this picture. So it actually showcases what actually is happening in the initial design domain. So we have, let's say, the flow coming in from the top and it's exiting. We specify the static pressure at the outlet. And here the pipes are essentially fixed as fluid. So we do not touch the pipes. but we consider the inlet and the outlet manifold as our design domains. And if we look at the optimization problem, so what we are trying to optimize here, the expression might look a bit scary, but it's nothing essentially trying to minimize, you can consider as a pressure drop minimization in the two domains. And we have two constraints. First is the V constraint, which tells you how much material can you take. And secondly, NDF, which is nothing but how uniformly your mass flow rate is distributed among the pipes. Because an important assumption for any of the heat exchanger design method is that you have a uniform mass flow rate along the pipes. So we always want to make sure that this is met. And what we do is that we design this on an unstructured grid. So we have roughly 230,000 design variables, and we test it with an Reynolds number of 1,000 using different material fractions in order to see how does the design change. So here are the results for the two different volume fractions. So here I'm showing the ISO volume with zero point 0.8 porosity. It has some very interesting features. So let's go step by step. First, let's focus on the inlet manifold. So you can see in the inlet manifold, it has this tapering effect in both the cases where it starts to taper down towards almost zero as the end in order to accommodate that all the pipes get an equal mass flow rate, which is quite similar to the 2D manifold design that you find in the literature. But now, if we draw our attention to the outlet manifold, we see some very interesting three-dimensional effects. So what essentially is happening is that the manifold is trying to guide the flow by making it a turn so that it is able to follow the streamlines much better with respect to the chaos that we saw in the first slide. And you can see it is present in both of the different volume fractions. Uh, of course, in this case, less amount of material is allowed, so you see that this effect is much more prominent. And in order to see this, we can actually look at the mid-plane velocities, and we see this effect very clearly. First of all, we see that our system implementation is working quite well, so there is no velocity streamlines which are going into the solid part. And secondly, we see that effect of flow turning is present in almost both the designs, but in this case, since we are constraining the material more, it's much more sharper. As well as a result of that, you see that the velocities are much higher. So the net objective function is much higher in this case compared to the 50%. But nevertheless, this showcases the potential that we can achieve with this method for such design problems. Now, moving on to our second design case. So we consider only two-dimensional slides, and we consider a symmetry plane in order to further simplify our lives. And the inlet and the outlet regions are fixed. So we only consider and the middle part has the design domain, and we have again our optimization problem. Now, in this case, what we're trying to optimize is for maximum heat transfer, because here the objective is that the fluid is able to cool down the electronics or whatever is present underneath as much as possible. So in this case, we are minimizing the solid temperature while constraining again the amount of material it can use. However, in this case, we have an additional constraint, which is to make sure it doesn't go for crazy pressure drops. So we do want to optimize for thermal performance, but then if the pressure drop increases tremendously, it is of no use for us. So that's why you see that at J representing the power dissipation constraint is present. And again, we solve it on an unstructured mesh. In this case, it's a relatively smaller base. So we have roughly 10,000 design variables, and we solve it for around number 400. An important point to mention here is that here for this design case, we did not consider the thermal conductivity variation between fluid and solid because of the reasons that I will come back towards the end. But nevertheless, if you look at the designs, again, similar thing to follow in the case. The dark regions represent where the fluid can flow, and the light regions is where is the solid. So we can see it starts with a very interesting approach. Maybe the graphics are not very clear. So it tries to create these branching structures that you can see in the tree, but it doesn't have the capability to convert them. And as you start tuning your Q more and more strict, it quickly converges to a local optimum. And towards an optima, which is sort of reduces to, you see that it does have some branching, but it is not able to connect all the features. And we see there is two reasons for that. First is that we do not have any filtering or projection, which are two very important parameters when it comes to topology optimization. And secondly, since we do not have the thermal conductivity variation between the fluid and the solid, we are missing a part of the problem. But nevertheless, if we look at the actual design flow field results, we can see that it is able to actually make use of this hermetic heat transfer in the solid regions quite effectively, reducing the temperature. And of course, wherever there is the fluid cannot flow, you see these hot spots. So it's a work in progress, but nevertheless, it shows the potential that we can achieve already with this type of implementation. With this, essentially, we can move towards the conclusions as to what we have achieved. So essentially, we want to enable the engineering system design with topology optimization. So we have three development phases and three milestones. For laminar flow, we have achieved all the milestones. For turbine case, we have the code. We also have the verification. We are currently running a proper three-dimensional design case in order to close this file. And for the heat transfer part, we have the code, but we have some issues in verifying, and then we will move forward to the design case. And now, going forward, this is the issue that I think I've already been discussing with quite a few people here, is that whenever we introduce this thermal conductivity variation, we start seeing these MPI ranks in our flow solution, and we are not able to find the real cause of it. But this is something that we will be working on. And then moving forward, we'll also do implement the spatial filters of this porosity, and finally do one final case with turbulence, with heat transfer, three-dimensional, in order to really showcase what this can do. And last but not least is to prepare the documentation and create a pull request. So with this, I would like to thank you all for your attention.
Thank you very much, Sanjay. It's really impressive of what you achieved. And it's also very, enlightening the fact that you picked up an early development by Tom and then resorting on them, you basically progress. That's the power of an open source community. So having said that, a couple of questions. There are three. Let me give the first the floor to Maria.
Yes. Thank you for the presentation. I have a question regarding quantum manufacture and kind of these things you would like to know precisely where are the solid parts and where are the fluid parts.
Yeah.
But for instance, if you are at the point with so with this density of equals like 0.8, how would you decide if this is solid or fluid? How would that how would it work?
Yeah, I think that's a very valid point. So I think that's a feature of this method, or let's say a drawback of this method, is that where is your boundary? So a typical approach which is considered is that, for example, you have gotten this design, you take an isosurface, for example, typically it's zero point 0.5 because it's the middle region. You extract it, you do a body fitted mesh analysis, you compare your objective, you see is your delta that you wanted, and then you try to move forward with the manufacturing. But indeed, if it's zero point 0.5 or zero point 0.8, yeah, there is no one answer to that, unfortunately.
Perhaps a follow-up, would you consider also using like a binary approach instead of two?
Yeah, then we are moving towards level set approach. Yeah, so there are different methods. So one of the methods is, let's say, level set approach, where you're always in a discrete levels. So then you do not have these problems. Yeah.
Thank you. Taylor and then Josh, finally. Thanks, Sanjay, for joining this with regulations. Earlier this year, you presented the topic also the conference.
Yeah.
And there was still one of the issues that what the pipes for 3D pipe case were not necessarily always connected.
Yeah.
How are you going to solve this issue?
Yeah, so that issue is still present. So yeah, I mean, just for anybody's reference, I can go back and see what actually is the case. That's a very interesting point. Yeah, because for example, if you do this optimization on this plane in 2D, and then I design these manifolds, there is no incentive for the optimizer to make sure that these outlets are properly connected with these pipes. So you can have these one. So indeed, we still have that issue if you start reducing the volume fraction in 2D. But we saw based on our experience that when you go to 3D, there is sufficient amount of material present for the optimizer to not leave any space behind. Uh, and also another thing is that for these kind of designs, the volume, let's say the material is not so significant for us because here there's no thermal aspects. The only thing it has to do is make sure the flow is uniformly distributed and with as little pressure drop as possible. So yeah.
Thank you. Last question, John.
It's kind of alluded to it a little bit. I'm interested to know how sensitive your final solution is to your value of Q. And if you made any kind of assessment on how that changes case to case, or from 1 minute to the rounds to E and
Yeah, so that Q interpolation, you always have to start with lower Q because essentially, if you start, irrespective of the flow regime you are in, if you start from a very high Q value, your problem is very stiff. That means any change that the optimizer tries to make in the material, it just cannot, the fluid just cannot flow there. And then it just will quickly go to a local optima that does not probably make sense and can be highly governed by your constraints, for example. So then the approach that we always typically follow is that you start from a very low Q and then you start and then you constantly observe how your optimizer history and as soon as you see it starts to converge, you pump up the Q again and then you continue the process.
just a comment of putting. I'm quite interested to maybe call this video joint capability to calculate the sensitivity of more for the limit to control your simulation rather than having to, manually inspect the optimizer to say, okay, now it's done from the center.
Yeah, that could be interesting indeed.
Good. Thanks a lot.
Can I make just one final
Yeah.
comment? Because I saw something that I wanted to ask about. So the MPI boundaries,
Yeah.
you're seeing issues there. So that typically means we're not communicating something in the halos. So with the thermal conductivity, is there something new you're computing that requires neighbors that we're not communicating?
Yeah, so that's what we're thinking. So the confusing part here is that so essentially now the thermal conductivity is a function of porosity. So wherever the porosity is defined, we do the same thing for thermal conductivity. And the thing is that we do not see any of these issues in your porosity field or any other flow variable. It's just in the thermal conductivity that we see these kind of artifacts.
Yeah, we're probably missing something.
Yeah.
About communication. Okay. Or you could put it on the fly in the halos if it's only a point value, you could reconfigure it in the halos. So something I think.
Okay,
we could talk this time.
Yeah.
A comment. The case of the manifold is extremely relevant from an industrial point of view. Are you aware? I know Carlos should be aware that I am the supervisor of a PhD candidate at VTI who's doing experimental work exactly on that geometry. If you go back there, she's been studying the influence of the position of the inlet and the outlet valve. So you have a pipe here and a pipe there, and there are various ways of. But the interesting thing is that she has this set up fully instrument.
Okay.
So once you get to where you want to be with your optimization, I think it would be relatively easy to test.
Okay.
With the proof is in the pudding.
Yeah, that's good to hear. Thank you for that. Yeah.
Thank you for the last comment. I say let's conclude the session with another round of applause.
Thank you.
Please also conclude